Well, let's work on this side. Can we rewrite this? It's going to take a little bit of work, isn't it? Got to find the antiderivative of this. This is going to be, let's see, the antiderivative of 5 is, do you have that in your head now? 5x, okay. Minus the antiderivative of 1 divided by x. We just did it, so it's natural log, okay, natural log of x. Don't forget, put parentheses around it, integrate from 1 to 4. I'm going to keep all of this on the left side of the page, just so we're following down here. So now, let me take care of moving that just for the moment, okay. So now I need to go in and I need to put a 4 in here, and then go back, subtract, and go back and put a 1 in. So let's see, I've got 5 times 4 minus the natural log of 4 minus, put in the lower bound, 5 times 1 minus the natural log of 1. So that's 20 minus the natural log of 4 minus 5. Don't forget you subtracting a negative plus the natural log of 1. Do we know what the natural log of 1 is? We just looked at it. 0. So we've got 15 minus the natural log of 4. Okay? That is the what? Area under the curve. Okay, that's the area under the curve. Now, to keep things straight, I'm going to put this in green over here. If I have f of c, what's that mean? What do I do with f of c? Well, in place I got a x, I put a c. So I've got 5 minus 1 divided by c times 3. Let's see, that's 15 minus 3 divided by c. What am I trying to solve for? C. Can I do it? Well, let's see here. I've got this side reduces down to this. This side reduces down to this. What sits between those two? Equals. So that means then, therefore, 15 minus the natural log of 4 has the same value as 15 minus 3 divided by c. With me so far? We're just solving 2 expressions here. Jenny, you got to look on my question. Where did I get the 3? Remember back in the fundamental theorem, the width is b minus a. Okay? So, who thinks they can solve for c now? Go ahead and do so. Let's see what your answer turns up to be. Okay, let's see what we have here. Answer. Fifteens cancel? Do we agree? Okay, 15's cancel. So I have C equals 3 divided by the natural log of 4. Are we agreed on that? Now, let's get an approximate value for that. That's approximately how much? Because you know if we're going to use our inspires, they're not going to, on the graph page, won't give us the exact answer. Casey, do you have an approximate answer there? That's good. That's the approximated answer.
2.164.
Okay, so 2.164, if we just stop there. Okay, so that if we're looking at area now, that would be square units. Now again, remember, not all integration problems are finding area under a curve. There's lots of applications. Now, if we're going to graph this, I think I'm going to just go ahead and start it myself on this. So I'm going to put a new page in. And let's put in the function. What was it? 5 divided by, or 5 minus 1 divided by x. Okay. And we're integrating from 1 to 4. And it looks like 6 will be sufficient for us. So let's go ahead and change a window. So I'm going to go from -1 to 5, scale 1. And -1 to 6, scale 1. I can say scale 1. Okay. Now what I want to do is, let's build the, well, let's go ahead. Let's try this first. Let's go into Analyze Graph, and let's go down to Integral. And we're going from 1, correct? Yeah, 1 to 4. So get as close to 1 as you can. And go over to 4. Did we all get 13.8? Okay. Wait a minute. I thought the answer was what Casey gave us, 2.164. That's the value down here. Okay, so let's put a point. Let's put a point on the axis here, and we'll try to get as close as we can. Now, by putting a point down there, I didn't get coordinates, did you? I didn't either. Okay, so how do we put coordinates on a point? Go to Menu, go to Actions, go to Coordinates and Equations, and we'll just point to that, and now we can see the point there. Okay. Now, I need to probably change those coordinates, and I'm not going to put in what you gave me, Casey. Instead, I'm going to put in the exact value. What is the exact value? So I need a fraction. So I need to go into a fraction, and I'm going to put in, where's in my place there, 3 divided by the natural log of 4. Okay, and it should come up to be what Casey told us, 2.16. We can extend that if we need to. What's the mean value theorem tell us? If you build a rectangle, the area, okay, not they will come, but that we can, okay, so let's build, I just had to say that. Okay, so let's build a rectangle, okay, and what's the base? Well, the base is going to go from 1 to 4, and how far up are we going to go? Now, that's going to be a guess, okay? Now, what we could do, we could go over, if you notice, I just moved the cursor, I go over here to about where I think that is. I could also do what? If I want to be more specific on it, put a point there. Yeah, let's put a point on the curve right there. Okay, and again, I'm going to change the coordinates here. And I'm going to make it a fraction again. And let's see, that was 3, excuse me, 3 divided by the natural log of 4. So that point now is directly above that input value. You know, I could draw a line to show that, but I think we can do that. Now build a rectangle, and when you go from 1 to 4, you can actually take the cursor and put it right there on that point to make sure you've got it. So that's what I'm going to do. Build a rectangle, 1 to 4, and come up over here. I'll go right to that point. Notice that the rectangle doesn't fit exactly the curve. And I can't even, it doesn't even look like, that little area that's overestimated doesn't look anything at all like it's identical to the shape that's overestimated. But what are we going to do? Measure the area of the rectangle. Good. Okay, let's measure the area of the rectangle. And what do we have for the area? Now, it didn't come out to be exactly the same thing. Why? Yeah, I don't know for sure. Yeah, I don't know for sure on that. Also, I'm going to try something else. I'm going to, remember that hovering thing we do? And so if I hover and then press the addition key, I might get a little closer idea. And I can see, well, they're not identical, but am I confident my answer is correct? I am. Okay. If I know that I did all my arithmetic and my calculus, finding the antiderivative, it is the same. That's the mean value theorem for integrals. Now, on that quiz, you think you might want to know this theorem? I would. Okay. So add it to your list of theorems that you want to make sure you know. You don't need to know this for the test on Tuesday, okay? But you will need to know this for the final quiz. Okay. That's what this theorem is all about. Fundamental theorem of integration, of integrals. That there is a point somewhere in that interval where the rectangle built on that point has the same area as the area under the entire curve. Okay. We now have, it's not known as a theorem, it's just called a definition of average value function on an interval. We just looked at the mean value theorem. We said mean is the same as average. Here we go, average. So how's this different? Well, when we look at the value of a function, we're looking at the input or the output values? Output values, okay? So on a function, I could have, on a function, whoops, let's try this again. On a function, I can have a lot of, all of these represent function values, okay? Infinitely many function values. What's the average output value, though, along that curve? That's what we're going to talk about, okay? That's what we're going to determine is if I have a function and I know that the function value is the output of that, what's the average output value along there? Okay. Function is integratable on a closed interval. Then the average value of the outputs, if you want to substitute the word outputs for F there, be my guest, the average value of the outputs on the interval is given by this. So we're taking the area and dividing by the width, okay, the interval there, the width. Okay, so let's see what we've got here. I think what I'm going to